Thank you for joining the Persistent Memory Trends panel. We have a distinguished panel today, which is a follow-on. We did a webinar in early March talking about persistent memory and where it's going, where it's been. And we wanted to invite those same panelists back today. We are missing one panelist today, which is Gary Kotzer from Marvell. But we certainly have a distinguished panel. I'm Dave Eggleston. I'm the moderator for today. I'm involved in business development in the licensing division at Microchip. We also have Pekan Gupta. Pekan is the business strategy specialist from Intel in the FPGA group. We have David McIntyre. David is the director of product planning, business enablement at Samsung. And Andy Mills. Andy is the Senior Director, Advanced Product Development at SMART Modular. So, gentlemen, thank you for joining once again. Appreciate your involvement in this panel. And when we talked last time in the early March, the persistent memory, we talked about kind of this, what stage we're in and how NAND and DRAM are being combined in new ways. And I kind of liken that to almost a Cambrian explosion of new ideas that are coming around, a lot of experimentation. We haven't quite found the right combination. So want to start there. I will mention to those who are watching this live, the Slack channel will feature live Q&A. We're hoping all our panelists will be able to answer questions through that Slack channel. So back to the main point, persistent memory and this combination of prevailing memory technologies. We're going to just do a quick speed round and I'll go in alphabetical order. So Andy, just your comments about, how you see that moving forward here with persistent memory. How are we combining technology?
I think there's going to be a lot of, NVDIMM has become a fairly stable, technology now in the industry. People understand it. They've been able to deploy it. It still hasn't taken over primary storage, in that sense. So, but it's certainly, carved out a pretty good, strong, I wouldn't call it a big niche, in terms of write back caching and storage, protecting metadata, any important data you want protected from power failure at memory speeds, and I think that's the key requirement. So I think looking forward, we see CXL as a key evolution of that technology, both from a single device perspective as well, from a pooling perspective. There's lots of good things happening there, and I think that's where we're going to be focusing a lot of our energy going forward. Certainly.
Let's hear from David. David, sure. Samsung's certainly doing a lot of experimenting with NAND plus DRAM in different products. How do you see persistent memory moving forward here over the next 5 to 10 years?
Yeah, I think it's putting more smarts around what the applications require, perhaps tiering. Persistent memory has had a challenge in scale out over the years. And so the ability to complement persistence with standard DRAM and storage might be a more practical way to go. So as Andy was suggesting, for things like metadata, where persistence may be a stringent requirement, maybe you don't need to have a terabyte worth of persistence. So by developing working hand in hand with the application developers themselves provides a means of perhaps saying, okay, how much persistence do we really, really need given the current state of today's technologies?
Got it. We'll come back around on that topic and drill more into what is the role of persistence in compute. Pekan, how is Intel and the FPGA group enabling this new rollout of memory devices, including persistent memory?
Yes, David. So effectively at Intel, we think persistent memory is more as an architecture, which can have different forms of implementation. So we look at persistent memory as being something which can save data across the power cycle is persistent, and an architecture which gives you access to the data at cache line or byte level granularities. So with a single memory semantic load and stores, that's a memory. So combining the two tolerant, fault tolerant, as well as a memory semantic, gives you a persistent memory architecture. Now you can define that or implement that architecture through NVDIMM-N like implementations, where you have DRAM, which gets backed up on the NAND flash using a charge supercap or a battery backup power. You can have memory semantic SSDs, which I think Samsung demonstrated in one of their previous consortium. And at FPGA side, you can also think it as a disaggregated memory pool, where as soon as you lose power, the data is flushed out of your single chassis system or from your rack to another rack, which is power fault tolerant.
So let's focus a little bit more on this overlap between I/O operations and memory operations. They've certainly been very separate for a long time. You know, if we think back to the basic architecture, we had, you know, this block architecture of here we have compute and then we have memory, if we think of the von Neumann architecture, but we've taken that memory and now separated it into I/O operations and load and store operations. So Pekan, coming back to you on that, how do you see these two, the line between them blurring, especially as we start to talk about bringing persistence into the load and store domain? What kind of issues does that create for the compute system?
So, David, a key difference between what we call as an I/O and the memory semantics is, one is the data width or the granularity of data access. You should be able to access the data at cache level granularities, and it should be directly accessible. That means there should be no driver layer in between, which will add another hop or do a retranslation. So memory semantics are always executed directly from the CPU core to the memory device. That's a key aspect. Yeah, and latency is very critical. This is why the latency is very critical.
Yeah, we'll come back and talk about latency and kind of this, you know, whole spectrum of latency. But David, certainly the announcement that it's not a product, it looks like proof of concept from Samsung, this memory-semantic SSD is very interesting because it looks like both on the same wires, you have the same interface. You have both NVMe capability as well as CXL.mem capability, and you have both NAND and DRAM behind that. Talk to us a little bit more about how Samsung sees, again, this blurring between I/O and load and store memory.
So for memory semantic SSD, which we've demoed as a technology POC, the ability of providing semantics where we're actually tuning the memory and storage support to a specific application like AI, we've reduced the granularity. Pekan mentioned this. So for us, we're down to maybe 64 bytes or less of specific sizes versus having to deal with blocks beforehand. So it's a more efficient tuning of our architecture to support those applications.
And let's jump ahead now. I was listening to a podcast over the weekend all about AI, trying to learn as much as I can, whether it's OpenAI, Stability AI. There's a lot of variants out there. Clearly, this is an amazingly hot topic with ChatGPT dropping and people just starting to experiment with it. Andy, what does that mean for memory overall? And kind of break down for us what that means both for training and then also for inference. Are we looking at a scenario where the amount of memory is just going to need to explode to support AI? Or are these models, although the model sizes are getting huge, is the actual file size relatively small? And we expect to see that on our smartphone here in the future.
Good question. You know, there's nothing around the corner that suggests memory capacities are going to explode, but the applications themselves are exploding. Of course, I think I saw something the other day, as we're all learning, ChatGPT needing something like 100 trillion, you know, different data points. You know, and I think when you start to look at that level of data, it's pretty clear to me that tiered memory systems are going to become pretty critical. You know, being able to learn how to put.
And explain that a little bit more, because some of our listeners may not be as familiar with it, or they might be familiar with tiered storage. But how does that work for tiered memory? Because we really haven't had it too much. We've had NUMA, but that really hasn't been, you know, the whole multiple spectrum of tiers has not been adopted.
Yeah, I mean, typically we've grown up in a world where CPUs had one type of memory. You know, now CXL is open, you know, one type of memory associated with a particular CPU core. A tiered memory system implies you have several types of memory of different latencies and different capacities. So you're trading off, for example, latency. If you want something in the 10, 20 nanosecond range, you want it really close to the CPU. You want it fast, an HBM style memory, for example. And if you want something that's big in capacity, you're not so latency sensitive. That's another tier. CXL pool is a good example of that. You're going over.
So I want you to, I want you to come back on how this applies to AI. Let me just give a model here, though, that we discussed in preparing for this. We were talking about the brain, and we can even think of the brain short-term memory being like HBM, where you really value speed. And then long-term memory, we need that depth. So we need that scratch pad space that's fast, and then we need that depth. And then also talk to us about persistence. What role does persistence play? So please continue on how does this apply to AI?
So I think we're still learning a lot about AI, of course. There's no final answer here. It's just scaling so fast and so rapidly. I think we're going to see a lot of advancements and changes. I think you still have this primary near-term memory. We talked about this in the brain offline before, right, Dave? I think the idea being that you need to remember stuff real fast, get access to it very frequently. That's going to require very, very fast memory. And then you're going to need some form of persistence to part of that. You can't save 100 trillion parameters, right? But you can certainly save your algorithm or something like that, or the backup or the metadata component of that. So persistence still has that important role to play at very high speed. The question is, do you have things like persistence at HBM level, or do you have it at CXL level, or do you have it, you know, where does it fit in the system? There's a practical.
Yeah, so Pecan, Pecan was looking at the architectural implications here. What's your thought about that? Where does persistence properly reside? And is it still just an IO op over NVMe, or does persistence really need to move into the memory space as a load and store operation?
No, I think persistence, when we talk about memory, it has to be load and store. And that's something which is as part of the definition of the architecture. Now, if you talk about different applications like AI, within the AI, we have training and the inference. And I'm not an AI expert, but I'll try to share my thoughts about the inference part of it. When you're talking about inferencing, you do some operations at every layer and different layers. And that's where I think it's very important that instead of copying the data all through the from the device to the host and making an operation and discarding the rest of the data, it's more important that you move the compute towards in the device itself, so that you kind of build something like a computational memory device. We call it by different names like processing in memory, near data compute, and likewise. But the concept remains same, that you are moving the fixed pieces of compute, which can be offloaded into a small size functions next to the data, where the data is residing.
I got it. So David, yeah, talk a little bit about this. I mean, we see the background for each of us as compute and memory and storage. It looks like we are talking about all three interacting here in new ways. How is Samsung seeing this and exploring this kind of all elements, not just load and store, not just IO, but also compute, bringing them all together in different units?
Yeah, so Samsung released SMART SSD a couple of years ago, which has an FPGA sitting next to NAND flash. In the context of this discussion, as we continue to build out a portfolio and do some product planning on what makes best sense, you could envision bringing in memory as well under the same hood, along with an accelerator and the storage media too. So you can do tiering where the data resides, to Pecan's point. So, one example here is the explosion of data. A lot of it's happening at the edge, as we know, and that's still greenfield territory. There's an opportunity there to design and develop products that support those real-time analytic requirements, where you have localized memory storage and some type of accelerator device where the data is captured and where it resides.
Got it. So let's go back, Andy. We kind of tabled this discussion about this tiered memory, but now we're looking at something that could have, you know, a whole broad spectrum of latencies that are involved. And how are we going to handle that in these compute systems, whether it's, you know, CPU, GPU, DPU, ASICs, XPU, and what protocol is set up to handle this? Because right now, you know, DDR is predictable, deterministic, and we need something that's non-deterministic. CXL is looking to fill that role. Maybe talk about that a lot more, that whole spectrum of latency and how we're going to handle it.
Well, you got a couple of, you've thrown a couple of things out there, Dave, which is kind of interesting. You mentioned GPUs, DPUs, you know, there's now an associated processing, APUs. You've got all kinds of vector-based, MAC-based, you know, there's a whole new bunch of XPUs that are out there now, all trying to get access to memory. And back to Pekan's point, you don't want to be moving memory around. The whole point about actually, you know, computational memory is that you want to move the compute to the memory, exactly as Pekan said. And I think that in itself makes tiering challenging. It makes it extremely challenging because if you look at some of the
Why? Why? Yeah, jump into the problems there. Why is it so challenging?
Because tiering involves moving data. Right? What are you trying to get away from in computational memory, for example, is moving data. So computing, you've got to really pay careful attention to transitory data you're pulling into your system, you want to crunch on, you want to get that stuff, you know, done, and then the persistence aspect of that, you want to store the results somewhere, right? So, but tiering memory really implies that you're pulling stuff that's very free access, it's very performance right to the CPU, right next to the memory. It's got lowest latency and it can compute the fastest. And then the tiering element is as you start to generate your result, you're going to be pushing a lot of data out or generating a lot of results. They don't have to be stored in your most premium high performance memory. You're going to push that out to maybe a CXL tiered memory device, for example, you know, in looking forward, where capacity, it's got a far more capacity to take all those results. So if you look at the way compute works, it's cranking on a lot of data, it's pulling in a lot of data, then it's got to push out a lot of these, you know, hopefully summary results. So tiering to me implies that there's two elements to tiering. One is you've got the two different classes of storage, capacity and performance, right? Those are the two general capacities. There's going to be some gray in between. But then you've got the whole aspect of, well, how do you manage that? The application has to be aware of that, for example. Does that create a whole bunch of new application APIs? Or do you want to do, Memverge is a good example, how they virtualize, for example, the memory, so you didn't have to think about it. You just threw it at it and it would try and figure out under the hood.
Yeah, let's bring Pekan in on this, because Pekan, you brought up this whole issue of it's hard for software to get in the middle because there's not time if it's going to be load and store memory. So how do we handle this? And my understanding is CXL, you know, CXL up through CXL 2.0, the CPU is keeping track of where everything's located. And maybe that changes a bit with CXL 3.0. So talk to us again about how does software play into this if what we're trying to get is this fast execution? And then also, when we have these multiple devices, who keeps track of where the data is located?
So this is an existing challenge which we all are trying to solve in different ways and mechanisms. For example, if you look at some of the papers presented by Meta on the transparent page placement, they do the same thing. They try to move the pages based on the hotness of a page. They try to relocate the page which is hot or very frequently used, and they want to keep it in the direct accessible DRAM, which is next to the CPU, so that it has the lowest latency. But all the cold pages, they want to shove it off to the slower tier of the memory, which is on the CXL, but within the box or disaggregated on different fabric. So Meta is doing it in the same way. All the other companies, they are trying it in a different a same concept, but in a different implementation. And coming back to the question, how does software know about it? The whole idea of bringing CXL as a direct attached memory was the above application layer should be agnostic to what is going down in the hardware. That is the primary.
That's not what Andy said a minute ago. He just said the application needs to be aware. Sounds like that's a problem.
So the
Yeah.
middleware will take care of all the things. It's not the, it's my view that the end application should not change. And it's a middleware like where
I see.
Memverge hypervisor or something else like that would take care of
Yeah,
things.
you're right. You are right, Bakan, by the way. I think there's no right or wrong answer here. I think when we did tiering, for the last 8-10 years, we've been working on storage tiering. We had this whole problem associated with hotness of data, but there's a penalty for moving data, right? There's a penalty for moving it up and down the stack, and that can translate into overall worse performance, or in some cases better. So it depends on the locality of data. There's all kinds of different aspects like that. But I think when it comes to memory, the challenge is software does get in the way. If you add any software decision, and software implies the CPU has to get involved. If you have to do a look aside to get the CPU involved to make any kind of translation, then it becomes problematic. So I think there's a hybrid model there somewhere in tiering. It doesn't mean tiering doesn't happen. It just means it has to change form. And that's where FPGAs and hardware come and help, because they can do a lot of that translation with a very, very fast translation layer of some kinds. Usually in tiering, you need a virtualization. You need some kind of virtualization, and then some kind of background movement or caching or movement of data. And I think that's where an FPGA with memory can keep that load store semantic going at its speed with lowest latency, and do what we call fast remapping. For example, you're remapping the pages, or you're remapping the data, to the next CPU or the next guy that has to have it without moving it. So it's just going to change the way it happens. And back to the earlier comment about XPUs, I mean, we've been reading a lot lately about how there's a new classes of AI CPUs coming out, because the classic CPU von Neumann, I'll say it right one day, doesn't fit anymore for a lot of this stuff when it relies on you moving data.
So you're talking specifically about NVIDIA's Grace CPU architecture, or you're talking about something else? Are you talking about more almost AI specific ASICs, which a lot of people tried, but boy, the models just ran away from them.
We hear of various, and this is both industry, a lot of speculation now, but there are several startup companies, there's several small, other companies, hyperscalers, developing their own AI engines per se for a reason. And I think it's because the nature of the data has changed. Before you could get away with very fast, hot CPU, right? Generating a lot of heat, a lot of power to do what it needs to do. Now they're saying, hey, power is too much, it's just not acceptable. And the hit of moving data is too, so let's do the processing in situ on the memory.
Well, I think even Lisa Su from AMD was talking about that recently at ISSEC, that the next supercomputer, you'll need a nuclear power plant to power it if we don't make some changes. So David, that brings up good questions about, and I think Lisa Su also made the case for data movement being very expensive in terms of power. Clearly Samsung has experimented in all kinds of things from core to edge. And how do you see this? Where does data, should we move compute towards the data? Because you talked about the FPGA product that you had with an SSD to do computational storage, or are we still looking at this kind of vast pool of memory that all kinds of devices can access at different times?
Yeah, so, we talk about bringing compute to the data, absolutely. That's just more efficient deployment of resources. And the flip side of that, or the complementary side of that, I guess, is, you don't have to move the data up to the cloud or to a centralized compute infrastructure, because it costs money to do so. And especially with the green compute initiatives that are going forward, where it not only costs money, it takes an enormous amount of power across inefficient resources when you're moving data back to the cloud or back to a centralized location. So why not compute when you can for the hot data apps? Maybe it's video analytics where you have real-time security measures that you need to address. Why not have your compute resources there, and you can actually build out a brigade of compute resources. I call them edge aggregation points, where you have a field server or a cluster of servers that can deal with near real time compute requirements. And then for those auditing or post-processing applications, sure, send the data to the cloud, or if it's private data, to an on-prem location.
So just like we talked about this spectrum of latencies, you're also talking about a spectrum of compute and data movement. Only move data when we have to. So I'm getting the picture now. Go back to my comment of this Cambrian explosion. Certainly in hardware, we're mixing compute and memory and storage together in new ways. We don't know what kind of creatures were going to come out of that. A lot of that experimentation. Let's go back to kind of the central point. What role does persistent memory play in this type of new environment? And let's say all the way out to the end of this decade. What's kind of your vision on that, David?
Sure. So, latency requirements will continue to be more and more stringent as people get comfortable with real-time analytics and decision-making, and as those applications are deployed across smart cities and autonomous vehicles, where nanoseconds perhaps are some of the latency requirements that could be seen. Optics is coming into the planning cycle too.
But how about persistence? How does you mentioned several applications there, but how does persistence play an important role there?
Sure.
Or can Samsung makes HBM and DRAM and all the different types of volatile memory. So you're probably fine either way this goes. But why persistence?
Right. So think of it, if you didn't have the data, you lost the data and you have to restart the clock. That's basically the issue. So if you're able to store the metadata, or even algorithms that need to be available 24/7, then that's where persistence comes to play.
I see. Okay, so it's really to make sure, and then it has to be in memory, not not an I/O operation, as we talked about, in order to have that fast restart. And I think again, Memverge has shown many places where you can have that checkpointing and restart be important. Okay, Pecan, how do you see this? What is the role of persistence in this new environment where we're mixing all these different capabilities together?
So I see Dave, as two sets of requirements. One, yes, you need to maintain the data as a write cache log or something like in a database. If you are doing a transaction and suddenly your network goes down, you cannot afford to restart all the transactions again. It will have a very large blast radius, which will impact not just one customer, but multiple other customers and services which are linked together, because it's a very complex ecosystem of services and microservices which run a single service platform. So this is an important reason why you need a persistent data, because if your network goes down, or if any other misconfiguration or a hack brings down your system, or at least one system, the first thing you need to do is contain the blast radius. That means whatever transactions were in flight, park them, save them somewhere so that they can be restarted. That's an important reason. Another thing is, okay, now you have identified that something went wrong, you have to debug it. What caused the failure? And that is only possible if your logs and error security violations were stored in real time. Your IOs are too slow for that. And they can only be stored in real time if you have a persistent memory or some kind of a low latency memory, which is power cycle tolerant, attached to your system.
I see. So that's where persistent stays in the picture, because we have to have that capability. So Andy, bring us around on this. What does 2030 look like, and what role does persistence play?
I'd say I have to give you one thought that was you were going through, the guys were going through talking here, was it reminds me of 50 First Dates, that movie where she kept having to wake up every day and keep learning every day, versus someone with a photographic memory, right? Those are the two extremes you're talking about here. If you didn't have
Oh, I like that model.
you didn't have persistent memory in there somewhere, you know what I mean?
Well, that kind of works with our brain model too.
There you
Our
go.
short-term memory can be volatile and our long-term memory better be persistence.
And you don't, and what's interesting is you don't need, everybody doesn't need a photographic memory, right, to be successful. You only need to remember key points, and that's what persistence is about. I think persistent storage or persistent memory.
Yeah, I think that's an important point. Keep going, please.
And you know, if you look at all the different attempts to get to the photographic memory situation, you've got MRAM, you got nano, the nano carbon tube kind of guy. You've got all kinds of different things. None of them yet have given the promise of being able to be the same price or lower than the DRAM, you know, or anything like that. So we got to work with what we got, you know, and what we got is memory is the only thing that can go at memory speeds today with NAND as a backup to it, right? So that's your equivalent of taking a snapshot or being able to capture stuff or a picture rather than having full photographic memory. So I think I still see quite a future, you know, of using off-the-shelf standard RAM with some fast backup mechanism. You've got to remember stuff if the power goes out. And then you're going to have some interesting, you know, technology that comes along the way. NAND is important, and the evolution of NAND beyond that is important for us to be able to remember the big stuff, right? The permanent memory, you know, to make sure that we can stash away all the stuff that we've learned and we don't just lose it before it goes off to archive, you know. So I think it's just going to be there. It has to be there to remember just sufficient to be able to keep the process going. So when you get up and restart your day, you're not having to relearn everything, right? You're getting up with, oh yeah, I remember some of the key elements of what I need to do to get to the next step, right? And that's how I think machine learning and inference is kind of coming about here. So.
Got it. Okay, now we're going to do our wrap-up speed round. And these are going to be your final walking points. What do you want? It's going to be two things. Number one, what do you want the viewers to remember from this panel, point you made? And number two, what do you want them to do? What action item do you want them to take with this learning? So I'm going to go in inverse order. And I'll give another 5 seconds for Pecan to think about this. But that's going to be the 2 points. What's the key point that you made that you want people to remember? And then what do you want them to do? Pecan, to you.
Sure. So the key point I want the people to remember is persistent memory is not just one single implementation or a piece of hardware. It's a concept, it's an architecture, which can be implemented as NVDIMM-N, CXL enabled or SSDs, and also as a architecture over disaggregated memory. You can implement it with FPGAs today. That's
what do you want people to do about
it? Wearing my marketing hat, I would say go and look at the persistent memory or pooling solutions, which has memory accelerators attached to it on our website, Intel FPGA website, and you'll figure out many other options in the play than just memory expansion, which will trigger new ideas.
Great. Great. Like that a lot. Okay, David.
Sure. So what I would like our audience to remember with persistence is that take a look at the problem from multiple vectors, whether it's memory, compute, storage, moving the data, the networking part of it. If you step back and forest through the trees, look at, okay, what is the impact if I have to move my data back and forth? What are the inefficiencies and the cost impacts in doing so? Consider that. Same with, what is the key benefit in moving compute to the data? And what type of compute do you need when you move it to the data?
Okay, that's your point. Now, what do you want people to do? What action do you want them to take?
Work hand in hand with the application developers to understand the application requirements so we don't overbuild and we build something that is very fine-tuned and supports market applications, specifically AI inference for cloud to edge applications.
Again, with this kind of Cambrian explosion, experimentation, mixing different elements together, you're saying, let's find a product market fit. Okay, Andy, what do you want them to remember and what do you want them to do?
I think I'd like people to remember is persistence is not something that's going to go to every part of memory, right? It's a small part of the memory picture, as Pekan was saying, and Dave as well. I think the thing to remember is you got to carefully choose where you want to use persistence, and architect your system and your your application, to remember those things you really care about, right? Which is usually metadata or special in-flight data or stuff that you just cannot afford to lose. And you just have to remember that there's no easy answer. There's no solution coming tomorrow that's going to solve the photographic memory problem, right?
What do you want them to do?
I would recommend people start to look more carefully at CXL. I think CXL promises a lot of good from a persistent standpoint. We at SMART are looking at ways to make it a little bit more plug and play friendly. I think it's been a little complicated to deploy persistent memory. You got to think very carefully about it. So I think CXL offers some new options with E3S, stuff like that, to plug and play, NVDIMMs, for example, in that form factor.
And do you have a particular place you'd steer people to learn more about CXL?
Sure. Well, the CXL consortium is one, of course. SNIA is doing some great work on that, as well as, of course, we at SMART have some products. Pekan and David's company all have products in this area. Just educate yourself. I think there's multiple places.
Got it.
And I'll just add to Andy's comment. Rewatch 50 First Dates, so that you know the need of persistent memory in your life.
Yeah, well done. I like that. Okay, as we wrap up here, first of all, again, here's the names for all our presenters. And thank you, gentlemen, for doing a fantastic job. Not just a few bits of housekeeping. I don't plan on doing any cleaning out of this, but here's what SNIA would like you to do as actions. First of all, if you want a little more background information, we did record a webcast, which is really kind of looking at how we got here in persistent memory. And there's also events coming up, in-person events. Flash Memory Summit is coming up in August, and the Storage Your Developer Conference is coming up in September. I believe the Storage Developer Conference is also soliciting papers right now too in presentations. So if you'd like to present at either Flash Memory Summit or Storage Developer Conference, please look into those. In the SNIA Educational Library, there's a lot of information, including this video will be uploaded to it at some point. And if you'd like to get involved, here's the links for you to get involved in SNIA. And then also in particular, we have a SIG, a special interest group, focusing on persistent memory, and the companies represented here are members in that special interest group. Please join us there. And then final thing on this session, if you can please take a moment, rate this session. Of course, we want to get a 5-star rating, 555, or if it's 5 out of 5, hopefully that's not 5 out of 10, and give us that rating. So once again, I'd like to thank all our presenters here today with Andy, Pekan, and David, and appreciate your viewing and hanging in there with us on this interesting topic of persistent memory and where it goes in the future. Thank you.
Thank you.